Okay, let us start. So, we saw some initial properties of the Banach algebra. We looked at a few things and we proved that Banach algebra, where every non-zero element is invertible, is actually isomorphic to the complex plane, right. That was the Gelfand theorem, and that used the fact that spectrum of an element in a Banach algebra is non-empty, right, which was proved using the fact that resolvent is an analytic function and in conjunction with Liouville's theorem, right. So, we will continue studying Banach algebras. Today we will start with a beautiful formula, but let me define spectral radius for you first. Okay. So, let script A be unital commutative Banach algebra. Many of the things I say will be true even without commutative assumption, but for the time being we will assume this. Okay. Many definitions, for example, is valid even if the Banach algebra is not commutative, and one has analogues of many of the things I do even in the non-commutative set. Okay. So, if I take an element in the Banach algebra, we define the spectrum, right. So, the spectrum is all those lambda in the complex plane where lambda e minus x is non-invertible, right. Lambda minus x is not invertible. Okay. So, for an operator this coincides with the spectrum of the operator, right. So, it is the same definition. So, define the spectral radius, of x. So, we will denote it by rho of x. So, this is this is going to be the spectral radius. This is simply the supremum of mod lambda where lambda is in the spectrum, right. So, you look at all the elements in the spectrum of x and you look at the modulus and take the supremum, that is called the spectral radius. So, if you have seen this concept for operators, it is the same definition, right. Now, note that, so it immediately follows that rho of x, so that is the spectral radius of x, that is less than or equal to norm of x, right, because this whole spectrum is contained in lambda with mod lambda less than or equal to norm x, right. For any lambda for which lambda greater than norm x, we know that lambda e minus x is invertible, and so spectrum is contained in this set, and so spectral radius of an element is less than or equal to norm x. Okay. It can be strict inequality, we will see some of this later. But today we will start with this theorem. So, A is commutative Banach algebra, unital commutative Banach algebra and so on, unital commutative Banach algebra, and you take a point in A, an element in A, then we have this formula, then rho of x. So, that is the spectral radius, right, maximum of elements in the spectrum, that is actually limit n going to infinity norm x to the n 1 by. Okay. So, you look at norm of x to the n. So, x to the n is an element in A, it is x multiplied by itself n times, and then you take the norm of that and take nth root 1 by n and then take the limit. So, there are various assertions included in this statement itself. Okay. So, one is the right hand side, which is the limit actually exists, right. So, we do not know that to start with, we just know that norm x to the n to the 1 by n will be a bounded sequence, because norm x to the n is less than to norm x to the n by the Banach algebra property, and then when you take nth root of course is going to be less than equal to norm x, right. So, you will get some bounded sequence, you do not know if the sequence converges at all, right, that is part of the proof. Okay. Now, more importantly, this is actually a beautiful formula. Let us see why. On the left hand side you have rho of x. Rho of x is simply the spectral radius of x, which is the maximum of modulus of the elements in the spectrum. Now, if you look at the definition of the spectrum, it depends only on the multiplication, right, that is a purely algebraic concept, that spectrum, that you look at all lambda such that lambda e minus x is invertible. The invertibility depends on how the multiplication is defined, right. So, it is a purely algebraic concept, and so rho of x, which is the supremum of things in the spectrum, is an algebraic object. And on the right hand side you have the norm, which is an analytic object, and we are saying the limit of these things on the right hand side, which is purely an analytic object, is equal to rho of x, which is purely an algebraic object. Okay. So, there are two initially they look, the norm and the rho of x, they look unrelated, right, but they are related in this way. Okay. So, that is why it is an important formula to have. So, we will start with the proof of this. Okay. So, proof. So, first note that so some of this part of the proof you would have seen in some form or the other. You look at lambda to the n e minus x to the n. So, x is an element in script A, right, in the Banach algebra A, and lambda is some complex number. So, if you look at this you can factorize, right. So, this is like a to the n minus b to the n is a minus b into sum of certain things. So, you do exactly that, because since there is only x involved and identity, there is no problem with commutativity and all that. Even otherwise we are assuming the Banach algebra to be commutative, right. So, this is j equal to 0 to n minus 1 with lower homogeneous degree terms, right. So, that is lambda to the j x to the n minus 1 minus j, right. The powers should add up to n minus 1. N minus 1 minus j, right. You can of course write this as in the other way also, j equal to 0 to n minus 1 lambda to the j x to the n minus 1 minus j into lambda e minus x, right. So, that is a standard identity you have, a to the n minus b to the n equal to a minus b times that certain sum, which is a to the j b to the n minus 1 j. But this tells me something. So, it follows that if you look at this, it follows that if lambda to the n e minus x to the n is invertible, okay, so that is the left hand side is invertible, then of course, the right hand side is invertible because it is the product, but what are we getting, lambda to the n e minus x to the n. If I multiply with let us say y, I get identity, which means if I look at the right hand side, y times that summation j equal to 0 to n minus 1 is an inverse for lambda e minus x, right. So, lambda to the n e minus x to the n is invertible, then so is lambda e minus x, right. Okay. So, that follows there from this identity, and okay, let me take some space here, yeah, okay. So, is lambda minus x, that is in the language of spectrum, what does it say, that is if lambda to the n is not in the spectrum of x to the n, right, that is lambda to the n minus x to the n is invertible, right. That implies that lambda is not in the spectrum of x. Okay. In other words, that is if I write it the other way, lambda in the spectrum of x, right, that means lambda e minus x is not invertible, implies that lambda to the n is in the spectrum of x to the n. right. That is what this means. This is something you know in some form or the other, right. If lambda is an eigenvalue of t, then lambda to the n is an eigenvalue of t to the n, right. In the case of operators you would have seen this, right, a part of spectral mapping theorem or whatever. Okay. So, let us continue. What does this tell me? Hence, look at this lambda to the n. So, if I start with the lambda in the spectrum of x, lambda to the n is in the spectrum of x to the n, right. So, hence if lambda is in the spectrum of x, we get the inequality, we get mod lambda to the n. So, that is the modulus of this will be less than or equal to modulus of the norm of the element, right. So, that is less than or equal to norm x x, right, norm of x n, right. So, remember that any element in the spectrum is bounded by norm of the element in that Banach algebra, right. So, this implies mod lambda is less than or equal to norm x n to the 1 by n implies. So, now you can take the limit, well we do not know the limit x is. So, we have to take lim sup and lim inf. So, this implies this is true for every lambda in the spectrum of x, right. So, here I have any lambda in the spectrum of x. So, I can take the supremum of such lambdas, that is the spectral radius. So, spectral radius is less than or equal to lim inf, because I do not know if the limit x is. So, we put lim inf there 1 by n. So, that is one condition we have. Okay. Now, we will also get a reverse inequality using lim sup. So, that we have the other inequality as well. Okay. So, let us start. So, next let f be a continuous linear function, right. A star, remember, is the dual of A. So, this is just a continuous linear function. Okay. Then f of r lambda. So, remember what is r lambda? R lambda is the resolvent, r lambda equal to lambda e minus x inverse, right. That is a holomorphic function, we have seen that. So, r lambda f of r lambda. So, if I compose r f and r lambda, I am going to get a holomorphic function, right. So, is an analytic function, is an analytic function for mod lambda greater than rho x, right. So, that is what, in fact, on the complement of the spectrum, in particular on this outside this ball, right. So, if I look at a ball of radius rho x, outside this ball the resolvent is analytic, and if I compose with f, I am going to get an analytic function. Okay. So, now remember the norm x. So, the norm x ball will be something bigger than this, it need not be equal to rho x. Okay. Now, outside rho x, so if mod lambda is greater than norm x, right. So, outside the bigger ball, then we know how to write r lambda. So, r lambda is lambda e minus x to the inverse, right. This we have we can expand n equal to 0 to infinity lambda to the minus n minus 1 x to the n, right. We simply take lambda outside and then expand it, right. X by lambda has a norm less than 1, and so you can expand it in the infinite series. We have seen this before. So, hence this is something which converges in the norm, right, which converges in A, in the Banach algebra A, right. That means with respect to the norm, right. So, hence f of r lambda, well what would this be? Because the series converges in the norm, you simply apply f to it, right. So, if I apply f to the partial sums and then take the limit, right, that is because of the continuity and so on. So, this would be simply summation n equal to 0 to infinity lambda to the minus n minus 1 f of x to the n, right, because f is continuous. Okay. So, what have we got? So, outside this range, right. So, this is for mod lambda greater than norm x, right. So, I have a holomorphic function. So, let me draw this again. So, I have a smaller ball which is let us say rho x, and I have a holomorphic function outside, right. And in a slightly bigger ball, right, possibly a bigger ball, that is norm x, I know how the series looks like, right. Of course, then that Lorentz series will be valid for all lambda such that lambda greater than rho x, right. So, let me write it down. We already know, oh sorry, so this is the series for, hence the Lorentz series for f of r lambda. Remember, it is a holomorphic function outside a disk, right. So, it will have these negative powers of lambda, and that we know, right. So, for f of r lambda is summation lambda to the minus n minus 1 f of x to the n equal to 0 to infinity for mod lambda greater than norm x, and so the same series is valid for mod lambda greater than rho x, right, even though rho x is smaller than norm x. So, this is something you have seen in complex analysis, probably you have seen this for an annulus and so on. So, what you can do is you can do a change of variable lambda going to 1 by lambda. So, instead of going outside the disk, you will come inside a disk except 0, and then you can apply whatever you know from Lorentz series there, and you will see this is true. Okay. So, now the series expression is going to be valid for the bigger range, right. So, lambda to the minus n minus 1 f of x n f of x to the n for mod lambda greater than rho x, right. So, from here now we simply look at the series. So, series each term, since series converges, we know that the terms will have to be bounded. So, for mod lambda greater than rho x, we get modulus of lambda to the minus n minus 1 f of x to the n is less than or equal to some constant, right. So, the terms converge. So, all of them will have to be bounded by some constant, but the constant may depend on f, right. So, okay, less than infinity for some CF, right, but it may depend on f, right, because depending on the linear functional the coefficients are changing. So, you may have another constant, but this is okay, because I am looking at some expression like this lambda to the minus n minus 1 f of x to the n is less than or equal to CF for some CF, but this is true for every f in A star. Okay. So, it follows from, so now we can apply the uniform boundedness principle, right. So, it follows from the uniform boundedness principle, or a corollary to uniform boundedness principle, that lambda to the minus n x to the n norm of this is less than or equal to C independent of n, right, independent of n, right. So, what we are doing is we are looking at the set x to the n's and applying lambda to the minus n x to the n's, and what we have seen just in the previous line is that if I apply f to it, where f is from A star, then f of that is lambda to the minus n minus 1 x to the n, f of that would be lambda is a constant that comes out, and I have f of x to the n. So, I have this set of vectors lambda to the minus n minus 1 x to the n as set of numbers in the Banach space A is pointwise bounded, right. For each f in A star it is bounded, and so by uniform boundedness principle the norms of them will have to be bounded, right. So, something which you have to seen in functionals. Okay. Hence, so now we are in good shape, hence norm x to the n to the 1 by n is less than equal to c to the 1 by n mod lambda for every mod lambda greater than rho x, right. So, we will get that, and now you can take the limit. Of course, we do not know the limit exists again. So, we simply look at lim sup, right. So, take we get lim sup of norm x to the n to the 1 by n is less than equal to mod lambda, right, mod lambda, but for every. So, this happens for every mod lambda such that mod lambda is greater than rho x, and we will simply get rho x here, right, we can take. So, that is true, and 1 and 2 gives the result, gives the result. So, the spectral radius. So, now because it is lim sup x to the n to the 1 by n less than equal to rho x less than equal to lim inf, right. So, lim sup will be equal to lim inf, and it both will have to be equal to rho of x. Okay. So, we will go ahead. Now, we start what is known as Gelfand theory. So, we have finished various preliminaries regarding Banach algebras, but we need to go further. So, we start what is known as Gelfand theory. Okay. So, Gelfand theory consists of identifying or trying to identify these Banach algebras as function spaces, continuous functions on appropriate spaces and so on. Okay. So, that is the aim. Okay. So, that one can study them a bit more in detail, because they are embedded in concrete spaces like continuous functions on a compact space or things like that. Okay. So, let A be a unital Banach algebra, okay. Commutative, well, maybe commutative, I will put in commutative as well. Okay. So, as I said, most of these things do not need the assumption commutativeness, but in our course it is always assumed that it is commutative. Okay. A multiplicative linear functional, linear. So, linear I may not say, it is when I say functional, it is assumed that it is a linear continuous map. Multiplicative linear functional, let us say phi on A is an element phi in A star minus 0. So, it is a non-zero linear functional which is multiplicative. So, that is phi of x y is equal to phi x into phi y. Okay. So, it is like a ring homomorphism, right. So, we are looking at the finite structure of A now. When I say is a Banach algebra, there is a multiplication there, right. When we look at vector spaces, we look at linear maps, right, because that is what preserves the structure of the given space. So, A will also look at linear maps. Of course, it has a norm. So, we look at continuous linear maps. So, that is A star, but now A is a Banach algebra. So, there is an algebra structure which is multiplication, and we want to look at those morphisms which preserve the multiplication, right. That is why you have phi of x y equal to phi x into phi y. So, these are called multiplicative homomorphisms or multiplicative linear functionals and so on. Okay. So, we will study these this. So, now comes a definition which might be slightly confusing, because we saw spectrum earlier, and this is going to be the spectrum for the Banach algebra. Okay. So, let sigma of A. So, remember we define sigma of x where x is an element in A, right. Here it is sigma of A. This is called the spectrum of A, spectrum of A for various reasons, I will not get into it. This is simply the collection of all multiplicative functionals on A. Okay. So, that is all phi such that phi of x y equal to phi x phi I, and phi is in A star. So, it is a map from A to the complex plane, right. It is linear and it is multiplicative. So, x times y will be mapped to phi x times phi y. Okay. Phi x times phi y is happening in the complex plane. Okay. So, let us look at some examples, so that we see that they exist, right. So, examples let A be equal to C of x. What is C of x? So, this is all continuous functions from x to the complex plane, continuous, right, where x is a compact T2, right, compact Hausdorff space. So, that you have lot of continuous functions, and the norm is of course the L infinity or the supremum norm, right. So, the norm generally denoted by L infinity norm is supremum over mod f of x, where x belongs to capital X, right. You look at the supremum norm, then it is a Banach algebra, we have seen that. Let us look at multiplicative linear, we will characterize the multiplicative linear functionals on this space, but not now, but let us look at some examples, right. So, fix x naught in x. I take a point in x and I look at the map, consider let us give it some name phi, right. So, phi let us put x naught at the subscript, phi x naught at f is equal to f of x naught, right, for f in A. So, A remember is your C of x, that is continuous functions on x, which is a compact Hausdorff space. Any f is mapped to f of x naught. X naught is a fixed point in the space x, and simply evaluate f at that point, okay. That is your linear, that is obviously a linear functional, right, and so obviously multiplicative, because if I take f g will be evaluated at x naught, that is f of x naught into g of x naught, and so it is multiplicative. Okay. So, that is a trivial assertion. It is a fact that any multiplicative linear functional of C of x is going to be of this nature. So, we will prove that soon. Okay. But let us look at another example 2. So, another example we when we define Banach algebras, one of the examples we introduced was L1 of R, right, all Lebesgue integrable functions on the real line with convolution, right, with convolution. So, let me recall that. So, what was the convolution? I take f and g in L1 of R, the product. So, this is not the pointwise product, L1 of R is not a Banach algebra with respect to pointwise product. F star g is the product, that is the convolution. Okay. So, f star g at x equal to integral over R f of x minus y g y dy. Okay. It is commutative. So, this is also equal to integral over R f y g of x minus y, that is a trivial change of variable, right. Now, I want to define a multiplicative linear functional on this. Okay. So, you know that L1 of R is a Banach space and its dual is L infinity, right. It is identified with L infinity in the sense that any L infinity function, any bounded function defines a continuous linear functional, right, by integration, right. So, f going to integral f phi, where phi is a bounded function, that is how the linear functionals will look like. Okay. So, it is going to look like that, but I want it to be multiplicative, that means the convolution should go to the product. So, define, so fix again, fix a T naught in R, okay, and define phi T naught, let us say, of f to be equal to integral over R f of x e to the I x T naught dx. Okay. So, everything makes sense, f is in L1, right, f is in L1 of R. So, I am defining a linear functional, well, e to the I x t naught is a fixed real number, x runs over real number. So, e to the I x t naught is a bounded function, right, its modulus is 1. So, this is a perfectly well defined continuous linear functional, right, f going to integral over R f of x e to the I x t naught. Now, if you look at the convolution, so this is a simple exercise, but let me give you one step. Phi t naught of f star g, right, I want it to be phi t naught of f into phi t naught of g, right. So, that is integral over f integral over r of f times e to the I x t naught, and similarly for g. Okay. Well, what is the definition of f star g? So, that is integral over r f of x minus y g y dy. This is f star g at x, right, and when I integrate against e to the I x t naught dx, right. This is what the left hand side is, right. I have two integrals and I have f of x minus y g y dy, that is f convolved with g, and I am integrating against e to the I x t naught. Okay. So, you check that this is equal to, well, it is easy to see what to do. So, because this e to the I x t naught has certain multiplicative property, you can look at e to the I, write it as e to the I x minus y t naught into e to the I y t naught, right. That will give me e to the I x t naught. So, this you can club with f of x minus y here, and I have g y and this, right. And remember that the Lebesgue measure is translation invariant, that x minus y becomes just one variable, and this will give me phi of t naught, phi t naught of f times phi t naught of g. Okay. So, this is called the Fourier transform. So, you can it is called the Fourier transform. So, if you know what the Fourier transform is, this is something you would have seen earlier, okay, called the okay. But remember L1 of R is an Banach algebra without identity, okay. So, no identity, right, but multiplicative linear functional still makes sense, right, because you just want multiplication to be preserved, that is all is there, right. Even though I define multiplicative linear functionals only for commutative Banach algebra with identity is not necessary in that definition. Okay. All right. So, we will stop here and continue in the next lecture.